Hydrogen, already in the past year, it was quite a central resource for many industries. And now more and more there is interest to use hydrogen as an energy source, as a green fuel, for example. And so we need to have new ways to supply this hydrogen, because if we rely on fossil fuels to maybe hydrolyze water and make hydrogen, then it will still be a problem, because the way we produce this hydrogen will not be very sustainable. So we need to find ways to try to produce it as green as possible. I'm Alexandre Holmes. I'm a postdoctoral researcher at Chalmers in Professor Wang's group, and I work mostly on how to convert the solar light into something that we can use. At the very beginning, I wanted to be a teacher in a high school, but slowly I was more interested in the research in chemistry field in general rather than the teaching part. One step after another, I really ended up focusing a lot on research. I'm naturally very curious. I like to also have challenges that take me a while, and eventually, when we manage or not to overcome it, at least, either we tried very hard and okay, we learn from it, or eventually we succeed, and this is quite satisfying.
When I was very young in junior school, I'm very curious. I want to invent something, and I heard from my teacher that if you want to be an inventor, probably you should be a scientist or professor. So since then, this has been my dream. My name is Ergang Wang. I'm a professor in the Department of Chemistry and Chemical Engineering. As a chemist, I feel I have the freedom to make something really new. I can use my mind to design some new materials with special properties that has never been developed in the world. So I'm a polymer chemist and focus on development of different kinds of polymers. One special class of polymers is they are semiconductive. This field also called organic electronics. That means we can use organic materials to replace inorganic materials to make electronic devices. What's related to this hydrogen generation is that we just use these semiconductive polymers as a photocatalyst to generate hydrogen from water.
What we do can be assimilated some ways to photosynthesis, because in photosynthesis a plant absorbs the light, which is energy, and conduct chemical reaction to have energy for its growth, and also in the other side produce oxygen. So this is photosynthesis. What we do is a bit similar in a way, that we use conductive plastics, so plastics able to absorb the sunlight, so absorb this energy, and then use this energy to conduct chemical reactions as well. And for instance, the one that we try to do is to have this conductive plastic able to, from water, produce hydrogen, just from the sunlight. Inside here, virtually, is a conductive plastic in water. So the yellow-green color, depending on your affinity, is in fact the conductive plastic. And on top of it, you have light, which is coming in. The light that we have is simulating the sunlight, what we would have outside. So what we do is we shine light inside of this little reactor where we have the conductive plastic in water, and hopefully over time we will have the production of hydrogen, which will accumulate, and we will see the generation of little bubbles of hydrogen which will rise. So the hydrogen we produce, these little bubbles, they will go inside of this headspace, so where there is no liquid, and virtually then everything is injected in this instrument, and which will tell us if it's hydrogen first and how much we have of it. And depending on that, we can know that this material we will be producing a lot of hydrogen or a little bit, and we can then quantify how efficient is this conductive plastic for this application. What we do for now, we produce hydrogen, but we use vitamin C to produce this hydrogen. If you make a simple calculation of how expensive is vitamin C, how much money you get from the hydrogen you produced, the balance is negative. So one of the big problem we are working on is how to replace this vitamin C to have something which makes this hydrogen production really viable also in an economical point of view. Because sadly, this is one of the important points for application in a large scale. If the cost to produce it's too expensive, no one will be interested in doing it. Even so, it's more sustainable.
In 20 years, I hope we can really develop the photocatalysts that can split water directly. Just use water and solar energy, and our photocatalysts, we can produce hydrogen and oxygen at a very low cost. We could also use this kind of photocatalyst to degrade some pollutants in water like PFAS and antibiotics, and hope that I can really contribute to a sustainable society.
I really like what I do, so I'm lucky enough to really go to the lab and enjoy always. So I wish to continue in the same direction, maybe to solve more problems than create new problems, but yeah, I think this is what I hope for.
So every time when I talk with students, I feel, they always make something interesting, something new. I was inspired by what they have done. During the discussion, we always generate some new ideas. We're all excited about that.
I'm blessed enough to have like a supervisor which is giving me enough freedom to try whatever I want to do. So in the lab, it's really nice, really fun. The lab mates that we have here in Chalmers, we often try to do things together to have this kind of collaborative works, because we all enjoy what we do, so it's nice if we can enjoy together.
But it sounds like you're having fun.
Yeah, I mean, I do.
Yeah.
Otherwise, I think I would not be here if I was not having fun.